In AD 79, a thriving city of 20,000 people went about their daily routines. Less than 24 hours later, Pompeii was erased, buried entirely under millions of tons of ash and debris from Mount Vesuvius. The consequences of such an event can be global. When Mount Tambora erupted in 1815, it ejected enough sulfur dioxide into the upper atmosphere to cool the planet, causing widespread crop failures and a year without a summer across Europe and North America. A volcano functions as a planetary pressure valve, a vent where molten rock, gases, and ash escape from the deep interior to the surface. Human civilization lives on a thin, solid seal. Beneath it, a massive thermal engine operates at temperatures high enough to melt rock and erase cities. That engine is fueled by Earth's internal structure. Beneath our thin crust lies a massive mantle and a core burning at 5,400 degrees. Here, mantle rock melts into magma. Less dense than solid rock, it rises and collects in massive underground chambers. Inside these chambers, dissolved gases like carbon dioxide and sulfur expand. Much like a shaken bottle of soda, these gases build internal pressure against the surrounding rock until cracks begin to develop. When the crust can no longer contain that strain, an eruption occurs. It is the mechanical result of planetary pressure seeking an exit. These exits are not distributed randomly. They occur primarily where the Earth's tectonic plates interact and fracture. At divergent boundaries, plates pull apart to let magma rise and fill the gap. At convergent boundaries, one plate subducts beneath another, dragging water into the mantle and lowering the melting point of the rock to generate new magma. This tectonic activity is most concentrated in the Pacific Ring of Fire, a geographic system that contains 75% of the world's active volcanoes. The location of these mountains provides a visual map of the structural weaknesses in the Earth's shifting crust. Magma reaching the surface builds four primary shapes: shield, stratovolcano, cinder cone, and lava dome. Their architecture depends on magma viscosity. Fluid magma creates the broad slopes of a shield volcano. Thicker magma traps gas, resulting in the steep, highly explosive stratovolcano. Because stratovolcanoes trap immense pressure before they blow, they represent a significant risk to the large population centers that often grow around their base. At the top of the scale are supervolcanoes, which feature magma chambers so massive that an eruption can release enough debris to impact the global climate for years. The physical shape of the mountain indicates the exact chemical viscosity of the magma within and how violently it will eventually blow. While lava flows move slowly, primary threats are pyroclastic flows, clouds of gas and rock traveling at 700 kilometers per hour, and razor-sharp ash. India sits away from the major fault lines of the Ring of Fire, but it still maintains a volcanic presence. Barren Island in the Andaman Sea is the nation's only confirmed active volcano, still venting steam and gas from its cone. 66 million years ago, India was the site of much larger eruptions. Massive lava flows formed the Deccan Traps, creating vast volcanic provinces that some scientists believe contributed to the mass extinction of the dinosaurs. Even regions far from modern plate boundaries have been physically shaped by these extreme, world-altering geological events. In the modern world, an eruption triggers an immediate economic domino effect. Logistics networks stall, local tourism stops, and agricultural yields can be destroyed in a single afternoon. This departure board shows the impact of volcanic ash on global aviation. Because ash consists of tiny shards of glass and rock, it can disable jet engines mid-flight, forcing widespread groundings and massive insurance claims. This satellite view of the 2022 Hunga Tonga eruption shows the scale of underwater events. The explosion generated tsunamis and atmospheric shockwaves that were detected around the entire globe. Over millions of years, these same processes built landmasses like the Hawaiian Islands and created the nutrient-rich soils that now support global agriculture. This makes the volcano a primary builder of habitable land. Throughout history, they exist as both the ultimate disruptors of human industry and the fundamental creators of the planet's surface. Even though we cannot stop a volcanic eruption, we can forecast increased activity by monitoring the Earth's mechanical warning signs. Scientists detect rising magma by using seismometers to listen for earthquake swarms and gas sensors to measure changes in sulfur dioxide emissions. Satellites use INSAR to monitor ground deformation from space, tracking how the surface of a mountain swells as the magma chamber beneath it fills. Modern management systems utilize IoT sensor networks and digital twins of volcanoes to simulate potential eruption paths and lava flows. This forecasting technology informs local preparedness, including the creation of hazard maps and real-time evacuation alerts for communities at risk. Translating the mechanical signals of a constantly shifting planet into data provides the hours and days needed for effective evacuations. Thank you for watching. Learn, think, grow.